So all I've talked about there is all about lattice strains, and therefore, if you know the elastic constant stresses, what about plasticity? And this message at the bottom here in brackets, I probably should have put at the top in red letters or something, it's really important. It's a diffraction technique. You will not learn about plastic strains. A diffraction technique will tell you about the lattice, and that's a lattice strain and therefore an elastic strain. The plastic strain you can't know about directly, because if you imagine a small bit of crystal and you have a dislocation gone through it, you'll get a shearing of that block, but if the dislocation's left, you've just got a nice perfect lattice again. It's just that the shape of the body has changed. So there's a body strain but not a lattice strain. So all we can work out about plastic strain comes from the accumulation of dislocations that are a consequence of the plastic deformation. So we can imply things, but we can't actually really properly measure the plastic strain. And that's a really important point, and the literature is quite confused about it, I have to say. And I'm sorry to say that I think in places I've probably contributed to that confusion. So this is me trying to undo the confusion that I've So the way we've gone about this is to look at trying to assess the geometrically necessary dislocation content or density. And the idea here is that the dislocations that are not tied up in dipole-like arrangements will lead to a curvature, a distortion of the lattice, so that you'll get some curvature in there, some rotation of the lattice. And so the idea comes all the way back to Nye and Kroner. And if you imagine here a schematic, just a series of dislocations making some field, they're all the same size here. You can imagine the lattice as you go across that field will get distorted. It's a series of low angle tilt boundaries, essentially, I'm drawing. And so if you measure how quickly that lattice rotates in here, you know the Berg's vector, you can work out how densely packed those dislocations must be to make sense of it. And you can either do it with a picture and recourse to angles of tilt around a low angle boundary, or you can do it properly mathematically in here using Nye's dislocation tensor and curl of our curl A. So A is our distortion vector. If you expand it all out, as I have done in the past, because I'm not mathematically very able, so I had to write it out term by term, drew a picture for every term just to make sure I made sense of it. Because again, the literature here is really very confused and horrible in places. And if you are interested in this, I would really recommend this paper that's come out recently from Felix Hoffman, Rima Das, and Ed Tarleton at Oxford. I think now actually, well, it was out as a preprint on an archive. I think it's now out, properly published. And they've sorted their way through this and unpicked to some extent the mess that's in the literature. There are different ways of writing down that curl. There are pre-curls, post-curls, and other ways of doing it. And they all look slightly different, and they're all rather confused. Coming back to what we can do. So here you can see there are rotations here, and how they vary the position, so rotation gradients or lattice curvatures. But the strains also vary from point to point. And so for full description, you need to have those in there. If you think about an EBSD map, though, we can't measure things along the direction into the depth of the sample. So some of those terms I have to cross out. So anything that's got a d by dx3 means variation with depth into the sample, and I can't measure it. So those terms are inaccessible. And the trouble is, if I have both, if I have to worry about lattice rotations and elastic strain gradients, it means actually I can only get to that final column in there, if you like, of the 3 terms out of 9 by 9 terms. Fortunately, though, in almost every system we've looked at, and only almost every system we've looked at, the lattice rotations are by far bigger than the lattice strain gradients. And so we can forget about the lattice strain gradient term. And because of the different symmetries, the different makeup of those two terms, there are actually rather more terms accessible if we just think about the 9 terms. So actually there are, well, it looks like when you look at this, there are 5 terms, but actually these 2 in here, you can also look at the difference between those 2 terms. So there are 6 things that are recoverable in here, which makes sense. You're making rotation measurements around 3 different axes and how they vary with 2 directions on your map, so there should be 6. I'm going to jump to an example, I think, rather than doing the abstract one. Although I will just point out, so we've got 6 constraints in here of lattice rotation gradients. And we've got, well, in many cases in the metallics, we'll have lots and lots of different dislocation types we're trying to solve for the dislocation densities of. There are no unique solutions, and it turns into a horribly ambiguous problem. And all you can do is find a lower bound solution. What's the minimum dislocation content that can support that lattice curvature? This is work we've been doing with colleagues in Earth Sciences, so Dave Wallace, who's now moved and is in Utrecht, and Lars Hansen, a colleague of mine in Earth Sciences in Oxford, looking at deformation of olivine. And so Steve put some slides up about this, which is good. So again, the cell for olivine is a much lower symmetry thing than we're used to in the metals. Stephen said that was a complicated problem. Actually, for this analysis, it's a real delight to find this, because it means there are fewer dislocation types that I have to worry about. And so the dislocation types, because this cell has got a very long B axis in here, I tend not to have dislocations with a Burgers vector along the B, because they're just big. B squared, GB squared, then becomes too big. They're an unfavored dislocation system. So instead I tend to get the dislocation systems that I've got in here. I can have dislocations with a Burgers vector along A in here, which could slip on this top plane here, this B plane, or this plane here, this C plane. Or I can have dislocations with a Burgers vector along C, and they can either be on this top plane here or on this plane here. And of course I can have screw dislocations of those 2 types, which kind of could either be slipping on that top plane or the side plane. But in total that means I've got 6 dislocation types that are likely to be found in olivine, which is great because I can measure 6 things. And now it's not an ambiguous problem. It's fully constrained. And at this point, I love rocks. Rocks are great. You knew that already. So the problem now should have a unique solution. The problem is actually hidden in this is that it's not true for all crystal orientations. There are some blind spots in here. And so what this is a fairly complicated diagram, but here's some inputs that we've put. So these are sort of stereograms showing the surface normal direction for our measurement. Okay, so imagine a crystal that's being rotated all over the place, or at least in our simulation, all over the place, and we can only recover the lattice gradients that are lattice rotation gradients that are in the plane of that surface. Okay. Here's an expectation, so I'm going to populate that one, and these ones are at 0. Green is 0, red is a high value. So if I say that I've just got that dislocation type in there, and then I try and recover from the measured lattice rotations that I would get, so I can work out what lattice rotations I get from this in a perfect crystal, then I can constrain things to be constrained, that I can only measure along the directions in my surface plane. Then you find that actually there are little blind spots in here. And they're blind spots because I don't have dislocations threading through the surface. Okay? So they don't contribute to any of the terms that are measurable in my lattice rotation. The columns in here are different ways of trying to recover that, and the best one, hopefully, you can pick out is this one in here, which which is using a pseudo-inverse and our 6 constraints. And effectively it works really well, apart from a couple of blind spots in here where, as I say, we're not going to measure the curvatures that those dislocations would generate. So we have to be armed with a little bit of forethought just in case we end up in a falling down. But here's some examples looking at olivine. So this is two different crystals in here. Two different crystals in olivine, loaded in compression along different axes in here. So hopefully you can pick out some here. We're sort of compressing between these two possible slip directions here at roughly 45 degrees. These two possible Locus vectors again at 45 degrees. There's a rotation between the two. Here are the lattice rotation maps that we found. So this is a rotation about an axis coming out of the board. This is a rotation axis that runs vertically in the frame. This is horizontally in the frame. And you can see quite different configurations between the two. If you go through the GND analysis, then you can start looking, this is our first case here, you can start seeing, well, there's one set of dislocations that runs through here, and they're kind of the dominant thing, they're the higher dislocation density. But hopefully you can also pick out that there's another set with a lower dislocation density, and actually a rather finer spacing between the features that you're seeing here, running this way. If I compare that to my other crystal, rotated and loaded in a different direction, and here again you can see two sets of dislocation features. So these are quite highly intense, high density features in here, quite well separated, and then there's a second set of features in here that run across the other way. And this all ties into the activation of the different Locus vectors that we'd expect to see. Okay. So, more by luck than judgment, I think that's pretty much my final slide. Thank